Good afternoon. I'm Professor Victor Ponce, and this is class 041 of CIVE 638, Sedimentation Engineering. And today the subject is sediment production. Sediment production. This is section 13.2 in engineering hydrology. That's my book, but we're accessing it directly through the web. Okay, so there are three aspects of sediment. And we need to study all three separately, and then we'll put them together, hopefully with the equations and so forth. The sediment routing, which is the ultimate application of this whole thing, is the sediment routing. We have sediment production, which is where we start. Prior to doing sediment production for the last couple of weeks, or for the last 3 weeks actually, we have been doing river mechanics. Why is that? Well, because river mechanics is a subject that begins everything, or rather everything is focused on river mechanics. But now we're going back to like subject by subject, sediment production, then we're going to go sediment transport, and then a little bit of sediment deposition, and then we're even going to do routing, sediment routing a little bit. Sediment routing is the routing of sediment. That is certainly the most complicated subject matter that we could deal with in sediment. When I went back to Colorado State back in the middle 70s, I signed up with Professor Simons, and he kind of delegated me to Dr. Khalid Mahmood, who was from Pakistan. And Daryl Simons had a big operation at there at Colorado State. At the time I was there, many PhDs were being produced every year. I was one of them, actually. So I got paired with Khalid Mahmood. And one of the reasons was, to be honest with you, because Khalid had said he had a project in Pakistan, and I was interested in traveling. I've always traveled. I've traveled all over the world, not all over the world, but in many parts of the world. So I wanted to go to Pakistan to see how it was, and I actually went there. I ended up spending 3 months in Pakistan doing my doctoral dissertation. That's not the story. That's not the story. I got paired with Khalid Mahmood, and he told me from the beginning, he said, Ponce, we're going to do sediment routing. And I, at the time, had never done any routing. I've heard about it, but never done it. So my initiation in routing was in sediment routing, which is the most complicated way. Water routing is easy. In my hydrology book, which is this book we're looking at right now, I covered 3 chapters on routing. First covered reservoir routing, then channel routing, and then finally watershed routing. So I was not unfamiliar with routing, but sediment routing was quite a challenge. And even to this day, it continues to be a challenge, even though since the time I'm telling you, 49 years have passed. I was a young man at the time. Now I'm not young anymore. But the point is that the subject today is sediment production. And as you know, I think I already told you, I decided to include the last chapter in my book, which is on hydrology. I decided to include sediment. And the reason was because when I wrote this book in 1989, I felt very confident. I had done quite a number of projects. I had not taught the subject, interestingly, because at San Diego State, there was another professor teaching, older professor, much older than I was, and he was teaching already sedimentation. This class was being taught by him. He was Professor Chan, but he retired in the year 2007, I believe, if I'm correct, plus minus 1 or 2 years. And then he was replaced by another person, and then after that person, for reasons that we shouldn't get into, was not at San Diego State. She left San Diego State in the year 2012. So since the other gentleman had already retired and the other lady was gone, then I took it. So I've been teaching this class for 10 years. Not every year, sometimes it's only every 2 years, sometimes depends. It depends on the needs of the department and so forth. But I would say over the last 10 years, I have taught this class 6 or 7 times. Always, of course, every time I teach a new class, it's always improving because we have all our material on the web and we're always adding stuff. Today, I added a couple of things to the syllabus for this week. And I always look at it prior and I say, well, what has come out new? And there are new things coming up in our practice. And we, as you probably know, are 100% web-based. Everything we own, we have it on the web. one way or the other, in one section or another. So let's go back to the subject, sediment production. Where does the sediment originate? Obviously in the rocks. Why is it important? Because it's part of hydraulics. Important why? I mean, specifically why? Because sediment gets in the way of our hydraulic works. Sometimes gets in the way, mean it could fill up the reservoirs. It could fill them fast. Sometimes we need to design debris basins, which are sediment holding basins, and we need to know the hydrology as well as the hydraulics. So sediment engineering, or sedimentation engineering, as our course is named, is very important, and it is the main reason why a lot of structures fail. Bridges fail mostly because of sediment problems, by the way, undermining of the piers and so forth. So it's an important subject. As I already mentioned to you many times, Albert Einstein told his son, Hans Einstein, to get into sediment engineering because it was something that hardly anybody knew anything at the time, 1928, and that was a good field to be in. And so Einstein did that, the younger Einstein, and he went on to teach. And then after he wrote that paper on the bedload transport back in the year 1950, he was kind of signaled or identified by UC Berkeley, and he went on to teach at UC Berkeley for 23 years, roughly on that order, until in 1973, I think 74, he passed away. But he is considered to be one of the, I guess you could say, important people in this field that we are dealing with today. And of course, we are going to get to talk about and to examine in detail his method, which is called Einstein's bed load function for sediment transportation. We'll get there eventually. The second part of the class. Okay. So, but all sediment originates in rocks. So how fast is denudation, the landscape denudation? So we can quantify that in terms of a depth per a number of years. Typically, for instance, we talk about the number of centimeters of denudation, meaning removal of rocks into sediment per 1,000 years. Like it could be 1 centimeter per 1,000 years. That's considered to be an average, by the way. 1 centimeter per 1,000 years, 1 millimeter per 100 years. That's not a whole lot. And yet there are places where there's a whole lot more than that. But that's an average. It's considered to be an average throughout the world. Has this been happening? It's been happening since the beginning. All the sediments originate in rock. How did that happen? Well, we already know that. I think we already covered that ground. There's weathering, there's rain, there's removal, there's changes in temperature, and all kinds of other things that contribute to altering the rocks, disintegrating them, and moving them by gravity. So all sediment is driven by gravity. Where is it driven? Downstream. Wherever there's a gradient, a hydraulic gradient, the sediment will move. Eventually, the sediment gets into the ocean. And once it gets into the ocean, it serves the purpose of feeding the food chains. So when you have a lot of sediment in the ocean, typically you have a lot of well-developed food chains, and that leads to a lot of fish. That's a well-known fact. Off the coast of Peru, you know Peru, the country where I originated, there is the Andes, and the Andes are very high. They're about average elevation maybe 15,000 to 16,000 feet, and perhaps in some places it even gets to 18 or 19,000. That's much higher than here in California. In California, we have mountains, but they're not as high, which means that there's a lot more sediment movement down in Peru than here in California, which means that in the ocean, there's going to be a lot more wealth of sediment, for sure. And that's the reason why off the coast of Peru, the entire coast of Peru, you have very rich fishing grounds. So I guess you could say Peru was lucky in the distribution because of the origin of this large quantity of sediments is the Andes, the location, the position in the Andes, right, covering from north to south, or even going into Bolivia and even going into Ecuador, by the way, the Andes. Okay, so that is a little bit of the story on where the sediment, what the sediment eventually do. Now, sediment is gold. What? Sediment gold? What are you talking about, Professor Ponce? Well, the real gold is the one we eat. And the sediments contain large quantity of a diversity of nutrients. And we eat nutrients every day. Because every time we have something to eat, that's organic matter which was formed by a certain amount of different kinds of nutrients. An apple is not a banana, and vice versa, and so forth. There are different kinds of nutrients that go into the production by nature of all the stuff that we call food. So without the nutrients, we couldn't have any food. We could have water, but we're not gonna, water does not have any organic matter that we could eat and disaggregate or consume, I guess you could say, in order to get energy. We can only get energy out of the organic matter, not out of water. Okay, so we can't drink water and pretend that we're eating, no way, okay? So it is the food that makes us, and the food is made out of sediment. So without sediment, there's nothing. That is what I mean when I said sediment is gold. Okay, and there's a lot more stories about this that are much deeper than what I'm covering right now. But hopefully we'll get to that. I talked a little bit about that in our course last year on environmental engineering. We have a theory called the 800 millimeter isohyet, which some of you will remember from last year, right? Cassidy, were you there? She's not there.
Sorry, I was on mute. Yes.
You remember the 800 millimeter isohyet, Professor Ponce talking about that?
Yes, I do remember.
Okay, fine. Well, I should tell you, and I'm not trying to brag here, but I'm the only one that talks about that subject because I developed it about 10 years ago, and I don't think anybody has followed yet. But that's a true concept, by the way. Around the 800 millimeter isohyet is where the diversity of nutrients is better for various reasons that we have explained in that class. That's environmental hydrology. Okay. So you should make a distinction between the amount of sediment eroded and the amount of sediment deposited. And that is true. It is not the same to confuse sediment production at the source to sediment yield at the downstream point. So when you as an engineer are doing an analysis of sediment at a downstream point, you cannot outright do sediment production because the sediment produced upstream is not going to be the sediment that is delivered downstream. There's going to be a percentage, maybe 20, 30, 50%, whatever it is your job to determine what percentage that is. So we have sediment or formulas for sediment production and formulas for sediment yield. Now the sediment production formula is more an ag engineering type objective, or has an objective. Why? Because the ag engineers that were working for the Soil Conservation Service and the ARS of the time, actually it wasn't the Soil Conservation Service, it was the ARS. What is the ARS? The ARS is one of many, many agencies of the federal government. It's called, or it stands for Agricultural Research Service. They employ about, I don't know, last time I heard, maybe a lot more now, 5,000 to 10,000 people working for ARS throughout the United States. The ARS scientists are the ones that develop these methods. Wishmeyer and Smith's formula came originally from ARS, and that is sediment production. So I would say that's a field of ag engineering. Not to say that we studying sediment could not study ag engineering. That would be too much specialization. Even though we're civil engineers, we still need to get into the sediment production. And I say that because my professor, and I don't mean to tell stories that are not 100% correct, but my professor, Daryl Simons, knew sediment transport, and he knew sediment deposition. But he didn't ever, that I can recall at that time, he didn't talk about sediment production. He didn't. He felt that was not his field. And he was correct. It was not technically his field. He was a civil engineer. Nobody ever hired him to do sediment production, so he didn't do it. Okay? But when I wrote this book in 1989, I decided to be comprehensive because I figured if anybody asks where the sediment came from, I'm not going to be able to say. And I knew it, so I said I'm going to put it all together. So here in this book, I talked about production, transport, and deposition, the three elements. Oh, in the end, we talked about measurements. That was the fourth element. sediment measurements. And we're going to be covering these 4 subjects. Okay? There's another story on that I will tell you later on. Not now. I think we're covering too much time or spending too much time on that anymore. So let me keep going on in here to say that, again, repeating, sediment production does not mean sediment yield. So as an engineer, you cannot take the formula for sediment production and pretend that it is sediment yield. It is not. And we'll get to make a distinction very clear distinction later on. Now, the next thing we need to look at is normal and accelerated erosion. There it is, a little bigger. Erosion may be classified as normal or geologic. And 2, 1, normal and geologic. 2, accelerated or human-induced. Normal erosion has been occurring at variable rates since the first soil and materials formed on the surface of the earth. That was a long time ago. Erosion, long time ago, what are you talking about? What time is it? I would guess it would be 4 billion years. Perhaps at that time water was already forming and so on and so forth. You know, the earth, the Big Bang, according to geophysicists, geovolcanologists that study the origins of the earth, they estimate that the earth is 5.94 billion years. So 5,940 million years is the age of the earth. Accelerated erosion occurs at a much faster rate than normal, usually through reduction of vegetative cover. Reduction of vegetative cover? What are you talking about? Well, human beings are experts in reducing the vegetative cover. We've been reducing the vegetative cover for almost, I would say, 3-4 million years? Yes. Well, let's not get anthropogenic or anthropologic here, but when the first species got out of the trees and they ended up in the prairie, that was about 4 million years, not billion, million. And that's, people actually, paleontologists and others disagree as to the actual time. Some people say 4, others say 8, or say 10. It doesn't really matter. It's too far behind. But the point is that since that time, the species that got onto the prairie and then developed into Homo sapiens in 3 million years has been changing the cover, the vegetal cover. And the change has been from trees to range to agriculture and to urban. And each one of these stages has brought in additional sediment movement. That is a fact. That is a well-known fact. So we are really producers of sediment in the river or wherever it is. Now, sediment, when it gets to the river or to the flows, doesn't necessarily have to be river. It could be a rivulet, it could be a very small channel, but eventually they get distributed and some of the sediment settles. Nowhere can we find, not nowhere, but in most cases, the sediment doesn't deliver itself 100% downstream, whatever downstream is. How do we know that? We know that because the valleys have been formed over the years. The valleys. And the valleys would not have been formed had it not been because of sedimentation. The Mississippi River Valley has taken maybe 3 to 5 million years to produce. I think that number is agreed by most people. And I don't recall at this point, but I looked at it recently. The depth of the Mississippi alluvium around Baton Rouge, Louisiana, is on the order of 7,000 feet. And don't get me on that figure because it could be 8,000. It doesn't really matter, but it's in the thousands, okay? That can be checked. All you need to do is Google alluvial depth of the Mississippi at Baton Rouge, and somebody will actually come out and say, yes, I know how much it is. But I've been looking at this number recently. I think it was 7, but it could be 5. Doesn't matter. Very deep alluvium on the Mississippi. Every valley has a depth of alluvium. And where did alluvium come from? From the rocks. How is it? From the sediments. How is it that we can have rocks and be developed into sand? That's pretty cool. And the answer is through abrasion, through disintegration, through chemical and physical action, the sand is formed and produced. I've talked about sand already last week, okay, how it is produced and how we use it. Even we use sand. Okay, quartz and feldspar are the main components of sand. So we have accelerated. So we've been producing erosion. Have we been producing erosion in the last 100 years? More so. The more development, the more erosion. Are we trying to control it? And the answer is yes. Societies, mostly in the United States, but maybe perhaps in Europe too, in other places, they're a little behind, lagging behind, but everybody's trying to control their sediments. We meaning the United States, we got our sediments out of the sediment transport and generation out of control in the 30s, and the entire Midwest, the states in the Midwest lost their sediment that went into the ocean and perhaps out there to Japan, somewhere, we don't know. But the point is that we lost a lot of sediment at the beginning of the 1930s. That was 90 years ago. That's when the federal government got smart and they decided to create the Soil Conservation Service. How fascinating. Soil Conservation Service to conserve the soil, because they felt at the time that basically they had a very bad experience in the 30s, and they were going to be losing more and more of the sediment. So it created the Soil Conservation Service in the mid-30s, and by 1940, by the way, the Soil Conservation Service produced this huge report, 80-page report, and they call it something like an initial step on research. That was their first report. Fascinating, enlightening, very well-written report that I have examined very carefully, and I believe we are going to be covering that report in this class. I believe so, later on. Okay, reading it, because it's important. I believe that book should be read by everybody. It's almost a book. Okay, so how do we calculate the sediment production? The first thing we need to do is calculate sediment production, because we don't know. Well, what happened was that there was a couple of gentlemen working with the Agricultural Research Service, which in the 1960s came up with this so-called USLE, Universal Soil Loss Equation. And it's called USL for its initials. It's a very well-known equation, very much used equation, very well respected equation. Not to say that it is, I'm going to classify this equation. I'm going to say it is not deterministic, it is not stochastic. It could be argued that it is conceptual, but I think it's mostly empirical. It's an empirical relation. The thing, it has a little bit tendency to be conceptual, because the authors conceptualized that there were 6 factors. They did conceptualize that. They chose 6 factors. After all that experience, these people, Wishmeyer and Smith, might have had 20, 30 years of experience before they actually developed this formula. Like Marcus, I know you guys don't know about Marcus, but Marcus in surface water hydrology, I talked about that yesterday. So they came up with this equation, which is a product of 6 factors. So each factor to be derived independently, multiplied, and get to the A. What is the A, and why do they call it A? Because it's an annual soil loss due to sheet and rill erosion in tons per acre per year. In order to do that, they identified 6 factors. You can imagine being Wishmeyer and Smith, or playing to be them. What are we going to consider? The first thing they considered was the rainfall factor, the energy of the rain. Okay, the second one was the erodibility of the soil. The third one was how long and how steep is the plane upon which this erosion, the sheet and rill erosion is happening. So they came up with a slope length factor. And for simplicity, they combined them into one. It's an LS factor, slope length, or rather length slope factor. Oh, interesting. Slope, okay. Then they also said, at the time they had already done those 4 actually, R, K, LS together, but they also said that there was a crop management issue that needed to be written in there. In other words, how good are you at managing the soil and trying to make sure that bad things don't happen. The idea is to not have the soil move. Wait a second. The soil is always going to move. then the issue is not move too fast. So what we want to do, although it's a difficult job, is to make sure that the soil moves at the rate nature said it should move. Because if it moves, if it doesn't move because you stopped it, engineers came in there and stopped the movement of the sediment, something's bad's going to happen downstream because the locations are going to be starved because the sediment is not getting there. So the issues of sediment, as you can see, you cannot fix it completely because you'll ruin it. It is an issue that's a touch and go. You got to consider that too much of a good thing could be actually counterproductive. And that's the real fascination with sediment. You lose if it's too much, and you lose if it's too little. So the crop management factor comes in there to try to control things from the management standpoint. And finally, the erosion control practice factor. There are methods for erosion control which are summed into practice. So they felt that it was necessary that in addition to the C, they would come up with another way, another knob, so to speak, to figure out what the erosion control practice or management of the practice. Okay, so then today we're going to discuss briefly the contents of this methodology. Like I said, it's a very common, very much used methodology. The only problem with this methodology that I see of is that it has a tendency to be abused. Why abused? Because it was developed for small basins, very small basins. It's not supposed to be taken and extrapolated to medium size or anything beyond what the developers thought that they were going to use. And you will see today that those are very small plots, parcels, because these people were agricultural people, and agricultural people are usually dealing with small parcels. For analysis, the parcels are always small. You never have a huge basin that you're going to study in one whack. It'll have to be in many sections, okay? So the rainfall factors, they consider to be the product of EI, where I is the energy and E is the energy and I is the maximum 30-minute intensity, and Wishmeyer and Smith came up with this map of the United States. Now, if you click here to display, I'm going to click here to display the map and show it to you so that we can get a feel of some of the numbers of the R factor. For instance, here in Florida, we have 450. The R factor is 450. I have an example in the book where the R factor is 185, which is over here somewhere in this state over here. I don't know exactly which state it is. Illinois or Indiana, I think it was Indiana. Over here, somewhere Indiana's over here. But if you go to the west, it's much less. You can hear 450, 100, and over here 50, 25, 75. Does it mean that it rains much less in California? And the answer is yes. And of course, in here we have EI. E is the energy, and I is the intensity. And we know that in California the rain is more intense. But that's a combination of EI. So E must be much less so that the energy, it must be that it rains much less in terms of full year. We're considering the full year over here because the report is going to be per annual basis, on an annual basis. So as you can see, these numbers for R in California are 20, 50, 75. And over here, they get to be in the Midwest, 200, 300. In Florida, 500. So you can say, oh, so there's going to be a lot of erosion in Florida. And the answer is no. Because they have a lot of rain, they have more vegetation, there's more cover, vegetal cover, and that is going to be considered by the method in some other part. Not in the energy of the rain, but in some other part, which in fact it does. The soil erodibility. The soil erodibility factors measure the resistance of the soil to erosion. It is defined as the amount of soil in tons per acre per year per unit of rainfall factor. That is per unit of rainfall factor. That is true. Because you're multiplying per unit of rainfall factor because it's a product. The formula is a product. Okay? So look at this. A unit plot is 72 feet with a uniform lengthwise gradient of 9%. So they took plots in the laboratory. They did this in the laboratory, by the way, in the ARS laboratory. I don't know exactly where. Somewhere out there in the Midwest. Okay? So you can see that these are short plots. 72 feet, that's nothing. And 9%, I wonder why they did a 9%. I have a feeling that they were always coming up with hills, and they wanted to do a 9%. I don't know exactly why. I wasn't privy to all the considerations that these gentlemen have put into their method. What we know is that they use 9%, okay? For 9% is the 9% of the slope. Values of K were found in here. So this is going to be the product to the original energy. So K times, is R times rainfall, R times K. As you can see, these vary from as high as 69% or 0.69 to as low as 0.08. No, 0.03. I'll be a gravelly loam. To be honest with you, I've never heard of that term. New to me. Not that I didn't type this equation sometime. I remember it was in the middle 80s that I typed everything that you see in there are typed. In the middle 80s, let me sidetrack it here because it's from my own history. In the middle 80s, there was no web. There was no word processors. Well, actually they were. The original word processor began to come out in the late 70s. And the word processing software, there was no word. The first word processing software was called, the second was WordStar, and the first one was WordPerfect, I believe, back in the early 80s. But it doesn't matter. I bought myself a computer and I typed the entire book. It took me a while. It took me about 1.5 years to do this. Create and type the entire book into the word processor so I could send it to the publisher for review. So that happened in the middle 80s, 85, 86 to 87, about 3 years. So all this stuff was typed. Eventually, when we decided to publish the book online back in the year 2014, 25 years later, I decided to publish it online because now, by that time, the web was fully ongoing. So how do we do this? Fortunately, we didn't have to retype it. All we need to do is to scan it and OCR it. OCR stands for optical character recognition. But it produces a dirty file, so we had to clean it. But cleaning was not as much work as typing it out right from the beginning. So we saved some time, but it took a while. Actually, I had students working and helping me out to do this at that time, 2014. The scanning and all this other stuff. We had to scan 600 pages. That wasn't easy, but we did it. As you can see, all this stuff is produced after that. Then we have the LS. I haven't talked about the LS. The developers of this method decided to combine the slope with the gradient. The length with the slope. And they produced this chart in here, which could be readily put into the computer, by the way. We have a calculator of this method. So this we had to put in the computer. So we go with the length of the plane, say 200, 300, all the way to 2,000. 2,000 from an agricultural standpoint could be normal. From a real standpoint, physical standpoint, 2,000 is nothing. But I'm assuming, of course, that they knew what they were doing, and they felt that they weren't going to go beyond 2,000 over here. And as you can see, they even didn't complete the chart. They had measurements for all the solid stuff, but the stuff that you see that is not solid, it's an extrapolation. It's a trend that they decided they would go follow it. Notice that they only get to 400, but they went all the way like trending out to 2,000. And then the slopes are indicated over here. 1%, 2%, all the way to 60%. Is 60% steep? No, we've seen 60% slopes out there. When you have hills, mountains, I'm surprised. Oh, I do want to say that all they were able to measure was 20%. But then they decided to extrapolate this thing. And to be honest with you, I don't know how they did this. I'm not going to quiz them or second thought these people on this. This is a very well accepted methodology. If perhaps because it is only the only one, by the way. So if you don't want to use this method, you have nothing to use. Very, very little left. Besides, this is a method adopted and supported by the federal government. And we know that that is an asset because you can always say, I use the method of the federal government. Word is there, else better, nothing, right? So that's why this method is considered to be the standard. crop management factor, I'm not going to dwell too much on it, but the crop management factor is defined as the ratio of soil loss from a certain combination of vegetative cover to the soil loss resulting from tilled continuous fallow. Okay, tilled continuous fallow is the worst case. If you leave the land in tilled continuous fallow, you'll have a whole lot of sediment production. If you manage it, then it will be reduced. So all these numbers have to be less than 1, and they are, as you can see. The proportions can be 45%, can be 402%, no, 0.04, or less, even that, less. There's smaller, there's values 0.003 in there, as you can see, for percent ground cover, and for different types and heights of vegetative canopy. So you can examine these, and you can take a look at this whole thing in here. I'm not going to get in there too much because it's not necessary. You can, on your own, examine this table and ask yourself questions about how could they have developed this practice. Erosion control practice factor, same thing. I already said this is the second knob in their equation. Physical, rain, soil, and length and slope. Those are geomorphologic and physiographic. But then eventually they got to the C, which is management, and P, which is practice. Control practice factor, which is this, by the way. And as you can see, we get down to 80% when you have a contour factor. The contour actually protects the soil by working on the contour. Because if you work across the contour, you have a lot of sediment production because the sediments very quickly go down through the channels. But the contour, on the contour, meaning at the same level, eliminates the strength or the gradient that the soil needs in order to move. So therefore, these numbers are lower than 1, as you can see. And then when you have even more specialized subjects, graded channel, sod outlets, and so forth, you get to a practice which may be even 10%. So that reduces the sediment to 10%. That's an order of magnitude. And yet, soils are like that. In soils, you have to accept 2, 3, even 4 orders of magnitude. I already talked about this, the variation. And that's the reason why we're not too picky about results that deal with sediment, because there's always going to be a large variation. We're used to that, by the way. I have a story on that, which I will endeavor to share with you later on, perhaps. I do believe I put it on the reading material. A story on how variability, we have to be humble when it comes down to calculating sediment, because there's large variability implicit in the computation. So the use of the universal soil loss equation. The universal soil loss equation computes erosion from upland watersheds on an annual basis. So it's an annual basis. That's why the result is called A. It includes the detachment and transport, but it does not account for sediment deposition. So in other words, it would say we're lifting it up and transporting it, but I don't know where it goes. It actually goes when it gets into the valley and finds a place to sit. Finds a place to sit. That's what's happening. All sediment in the world, what is it doing where it is? The answer is, it is resting. It is resting because in the next big flood, it'll move. It'll keep going downstream. Where? Where eventually? Into the ocean. Why is it that in the ocean we don't have a lot of rocks? Actually, we do. It depends on where you are. It depends on where you are. But typically, you don't have rocks, a lot of rocks in the ocean. Why? Because the rocks have been disaggregated as they move downstream. And there's enough time and space in there, presumably, to disaggregate the rocks. I have studied many, many rivers, quite a few. I studied extensively for a couple of years the La Leche River in northern Peru in the year 2008, 2009. I had a project over there for 2 years. And we found these huge rocks, diameter about 3-5 feet. And I think I've shown you at the beginning of this class, Rachichuela Creek over in the La Leche River. It's a tributary of the La Leche River. And they had these huge rocks, but we couldn't see them downstream. Within 20, 30 miles, they disappeared. Where did they go? Did they fly? No, sir. They disintegrated as they were coming down. How do we know that? Because it happens everywhere. Are there exceptions? And the answer is yes, 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 yes. There are exceptions. Under normal situation, the gradation of the bottom of a river would be continuous, meaning big rocks upstream, little sand downstream. And even if you get to the estuary, it wouldn't even be sand, it would be silt. So you go from big rocks, boulders, to gravel, to sand, to silt, as you move all the way from the hills to the estuary. Is that 100% correct? And the answer is yes, but there are situations which are exceptions where you have not normal situation, unusual, extremely unusual situations where you may have a river that has a huge bunch of rocks in there, and you don't know how that could have happened. Example, the river up there, I think it's a Snake River in Idaho. And to be honest with you, I wanted to go out there and take a look, but I could not. The chances did not come up for me to go out there, and I cannot go by myself. I got to go as part of a, how can I say, a team, students and stuff like that. I never actually was able to put it together. But in the last 10 years, I wanted to go out there because I got word in the year 2012 that there had been a huge event 14,000 years ago, which all but overflowed Salt Lake City. No, I'm sorry, not Salt Lake City. Salt Lake in Utah lost, oh God, the number would have been like in feet, it would be like 500 feet. 500 feet of depth in one event. How did that happen? It breached one of its walls, the wall that was protecting the height of the river of the Salt Lake. It breached, and I have a story that I'll eventually going to share with you if I have not done so yet. I think I did it already. Let me just say that if I haven't done it, I'll check, and if I haven't done it, I'll come back and show it to you. But the point that I'm trying to make in here is that particular event, which happened 14,000 years ago, carried a heck of a lot of sediment out of the breach. And it was so sudden that they didn't have the energy to disintegrate all of it. And it kept coming down, and it got stuck in the middle. So if you go to the Snake River in Idaho and transverse or go through the Snake River from one place to another, you'll find that there's a whole lot of huge rocks and boulders in the river and in the valley. So one wonders how this could happen. This is against what Professor Ponce just said, that the gradation of the river should be smooth and gradual from very large to very small. In this case, we have one case, the only case I know of that law is not satisfied. So it's a fascinating sedimentation problem. I wasn't there, but I went over to Google Earth and I decided to look for it, and I did find it. I did find the reach over in the Snake River in Idaho where these boulders show, and I took some pictures. So Google Earth helps us a whole lot. It's not the visit, but it is next to the visit a good experience. So the example of the universal loss equation, we have a calculator for the simple case and a calculator for the second case. So I'm going to use in here, I'm going to go to an example directly. So no, I am fond of my calculators very much. We did a lot of work. We started doing these calculators in the year 2004. And over the last 15 years, let's say, 15 years, we have done more than 300 calculators. We did it in everything. Anything that could be calculated, we calculated it and put it on our site. So we have about 380 calculators. Eventually, we translated some of them into Spanish and even into Portuguese, because I can handle Portuguese. Portuguese is only 20% different than Spanish. And also, I spent a lot of time in Brazil because we were doing a lot of consulting out there when I was young. So I learned Portuguese very quickly. So I have maybe about 50 calculators in Spanish, 50 calculators in Portuguese, a total of 380 calculators. So I'm very fond of my calculators. Unfortunately, there are not a whole lot of people that are doing this, which suits me. I don't really, I can't really push people to do what they don't want to do. But these calculators are very easy to use, and provided they are correct, they could be time saving, tremendous time saving. If you had to do this calculation by hand, it'll take you, I would say, if you're good, if you've done it before, it will take you 15, 20, 30 minutes. Because you're going to go into the graphs, you got to do the calculator, you got to make sure you did it right, and so forth. You can also do it in Excel. And if you're a good Excel person, you could cut it down to half the time. You still have to gonna set it up with the Excel and so forth. The only problem is that you cannot share the Excel. Well, you cannot share it on the web. I do not believe, I could be wrong on this because I don't deal with Excel, but I do not believe you can share an Excel spreadsheet and have others work with it and have others modify it. I don't think so. I could be wrong on this though. Because like I said, I don't work with Excel. But the point is that Excel has a drawback. The drawback is that it predates the web. Excel came out in the year 1991. It superseded Quattro Pro that had superseded 123. Those of you that are young, and I'm sure all of you are, don't remember what I'm talking. But the first spreadsheet that came out was 123 in the year 1881, I believe. Then it was superseded after 5 years by Quattro Pro, and then in the year 1991, 1992, Excel from Microsoft came up and they superseded all the other two, like Microsoft Word did the same thing to the other word processors. So they took over. Microsoft took over in the early 90s. Say 93, 1994, it was very well Excel. It was at that time that Tim Berners-Lee had decided to put out his code to access the web for everybody. And he did it freely, by the way. He gave the world the capability to get on the web through this code, this protocol. He called it a protocol that he called HTML. So Berners-Lee allowed us in the year 1993, middle of 1993, to get on the web. So, but it took a while for people to get on top of it. I remember that in 1997, I had a student come over from Turkey and said to me, "Professor, why don't you get into the web?" I said, "What?" I heard about it. I knew San Diego State was very active on it. But, you know, people drive their feet. I can drive my feet too. So in 1997, I was not there. I wasn't there. And then 2 years later, there was another student from Turkey, by the way. How interesting. 2 people from Turkey. Then one, a student, very smart people. They came over to me and he was working, and I don't want to get into details of how he got into work with me. That's another story, a 10-minute story. I'm not going to tell it right now. But he got over to me, and after we were working with him for a year, he did a thesis with me. He said, "Professor Ponce, why don't you get on the web?" I said, "I don't know anything about it." He said, "It's easy." I said, "Well, you teach me." And he taught me. He taught me in a couple of weeks HTML. Can you believe that? A student teaching a professor. Convincing a professor and teaching a professor how to use HTML. I still maintain a very good friendship with Cesar Khan. He's got me into this. 1998, 1999. But 1999, 5 years after Tim Berners-Lee had developed his methodology, or had actually put his methodology out for public use, because he had been working on it for 5 years. Okay, so finally I got on top of it, and once I got on top of it, I began to like it. I said, this is the future, if not the present at the time. Very few people were on the web at that time, by the way. There's nobody out there that can claim, let's see, that can claim more than 4, there's 6 plus 2. Nobody out there can claim more than 28 years on the web, because the web is only 28 years old, right? Even Amazon was developed in the year 1995, I think, 419, but you go back, check. Amazon and Google in 1998, 1999, all of them afterwards, after 1995. Professor Ponce was 1999. I got on the web in 1999 fully and completely. I decided I was going to get into this big because I felt that that was important and useful, and it was a game changer, totally, as you guys know very well. So what I'm going to do now is I'm going to run the online, okay, select Unix US customary, number of watersheds, 3 watersheds we have in there, put the drainage areas. I have already typed this over here. I typed it this early, so I don't have to retype it, because the computer has what they call a cache. A cache means, I don't know where that word comes from, but you know what it is. You heard it before. Cache, meaning something stored in there temporarily. So I have 38 in there, and slope and length. The slope and length is, all I need to do is type the first one, and the computer will remember the others. How easy, isn't it? 0.12, and it will remember the other ones, an erosion control practice factor, you got to be orderly about this. You can't just, do whatever. So I typed this morning these values and I had to run and I retyped it. Now I didn't retype, I just asked for it to retype it for me. Okay, and now I'm going to calculate the answer, and the answer is 1126 tons per year. Okay, 1126 tons per year right there. So I reproduced for you today as an example how easy it is to use this calculator when you're given all those numbers. So there's 3 ways to do this problem. By hand, and that would be not the correct approach, or creating your own Excel calculator, and I submit that it would not be the correct approach either. And the third one is to use Professor Ponce's calculator, which is out there freely available, or to go to some other calculator. We've been doing this for 15 years. So by this time, maybe there's other fancier, better calculators. Eventually, they're going to come out, you're going to have to pay for them, because that's just the way the ball bounces. Okay, they want me to pay for it. I don't want you to pay for it because I'm already paid by the state. I am an employee, a retired employee of the state of California. So I don't charge for this stuff. Okay, so that's the story on the universal soil loss equation. Now, but that is sheet and rill erosion. What is rill? Rill is a rivulet, or a very small channel. So it's not sheet erosion, but it's rill erosion. But I submit, and I have people that recognize this, that there's really no way out there to calculate rill erosion. Sheet erosion is what Wishmeyer and Smith presented us with. So everybody bundles it. It says sheet and rill erosion together, kind of, that is Wishmeyer and Smith's. That's the understanding that we have currently. So the next type of erosion is channel erosion. Do we have channel erosion? This is yes, of course. And channel erosion could be sizable. We have to calculate channel erosion, but it is difficult because it's spatially diverse and it doesn't happen all the time. It varies with the geomorphology, it varies with the hydrology. It's a tough thing to calculate channel erosion, but we recognize that it does happen. Channel erosion includes gully erosion. What's a gully? A gully is a huge channel that was recently formed. Like the channel, there was no channel. All of a sudden the channel appeared. That's called a gully. And I'll show you some examples later on. Stream bank erosion? Yes, there is stream bank erosion. I show you that picture at the River Apa over in Brazil, in the border of Paraguay and Brazil, where the river is meandering, and in order to meander, it's got to move the sediment from the bank. And it's got to break it up, and then it move it out, right? And I showed you that picture. I'm pretty sure I showed you that picture. Streambed degradation, could that happen? Yes. Look at this picture over here. Erosion to bedrock downstream of a sediment retention dam. And I'll have a chance to come back and explain this in detail. How do we know that there was erosion? Because below every deposit of soil, there is rock. Always, always. I already told you that in the Mississippi, it was 7,000 feet. So how do we know, how we can say that in the Mississippi there were 7,000 feet of alluvium? Because people have examined the bottom with geophysical aspects or rather methods, and they determined that the rock lies at 7,000 feet at this particular place. So this is a river which is called the Aguaje de la Tuna in Tijuana. In the year 1991 or 92, I'm not sure at this point, but it's in the video. In the year I think it was 93. In the year 1993, right, correctly, they had a problem over there. They had a huge storm, okay? It was an El Nino year, some weird El Nino year that had a huge storm. We have a video of the storm in East County, San Diego, at the same time that this happened in the year 1993, January and February 1993. So it was a regional storm covering San Diego, East County, Tijuana, which is right next to us. And they had this huge event, and the flood eroded the valley to the bottom of the soil. That means it touched on I believe this is rock. It's called shale. It's shale. What you see in there is shale. Shale is a type of rock. Okay? So we got in there, and we did a video afterwards back in the year 2012. I was invited to go over there. No, I think I invited myself. I have some friends over there, and I said, hey, can you take us over there? We don't know exactly where it is. And we did that video, which is a great video, by the way. I'll have a chance to show it to you later on. But I just want to tell you that erosion, bank degradation, or rather channel degradation, can reach datum, meaning the bottom. And this is an example. Okay, floodplain scour, yes, we can scour the floodplain, and other sources of sediment. Gullies are incipient channels in process of development. Is there any gullies in the United States? There are gullies all over, by the way. Gully, I consider a gully, the formation of a gully, to be a cancer. Why a cancer? Because it's bad. Because a gully means there's a lot of sediment being moved. And it also means that it's difficult to stop. Once the gully forms, it'll continue to go on. Why did it form? That's an interesting story and question. I will answer that later on. Why do gullies form? But once formed, it's difficult to stop. Not that it have not been stopped. We have had determined efforts by the federal government, engineers here in the United States, and other parts of the world, I may say, to stop gullies, try to stop the cancer, so to speak, okay? The gully sediment is delivered to downstream locations, and so on and so forth, and the sediment moves. Sediment is always moving. There is a certain truism in this. We have to let the sediment move. What we should not allow is to large quantities of sediment to move in places where there was no such movement. Because if that happens, then we'll have to contend with the deposition downstream. It would be like in a river. It could deposit in a river, and then the river doesn't carry any floods. Then we have to be called out there to figure out what to do with the river, because the sediment that is occupying the bottom of the river would be a problem, you see? So as you can see, there's ample situations for us working in this area of sedimentation engineering. It's a fascinating, very difficult subject. To me, it's interesting because I've dealt with this for so many years, since 1973, as a matter of fact. So there's 49 years that I've been working with this subject. Okay, methods for determining channel erosion. There's this formula 13.7, which is found in the manuals, but it is a very dumb formula. Why do I say that? Because it said that the sediment movement is equal to the height of the bank times the length of the eroded bank and the annual rate of bank recession. So those three give you a volume, for sure give you a volume. If you can find those three numbers, you will be able to calculate the sediment that was eroded and generated out of the bank. But in order to get that data, it may be difficult. Do rivers move? And the answer is, of course, they move all the time. The Apa River is moving all the time. Well, how do we know that? If you overflow or fly over, and the Apa is not the only one, by the way, but it's the one I'm most familiar with. If you fly over Google Earth on the Apa River, you're going to find it making very nice sinusoids, and you're going to find that the sand is in every curve. The sand is in every curve. What is that sand doing there? It's resting, because when the APA decides to straighten out, it is going to move that sand, it's going to move it to the next curve. It would take 10 years for that to happen, but it will happen. Okay? So that is a slow process. It's a time engineering process. Remember, I talked about that briefly already in relation to the work of my friend Carlos Rodriguez, who is doing sediment, or rather alignment, river alignment control in various parts of Colombia. Okay, accelerated erosion due to strip mining. Strip mining was something that was being done in the 70s. And I remember when I was at Colorado State, my professors had projects to do strip mining studies. So I worked on this quite extensively for a few years, I'm sorry. Strip mining is important. It was more important at that time. Now it isn't. Why? Because strip mining was for coal, strip mining for coal. And now we're not mining any coal. It's bad. It's a bad thing to mine any coal these days. So that business, so to speak, has come completely down, but not in the 70s and 80s. It was very active at that time. But barring strip mining, we have construction activities. And construction activities are going on everywhere. Everywhere. So the construction activities are generators of sediment. Now, in this country, we have regulations about that. We have the so-called best management practices. I don't know who invented that term. It's kind of a misleading term. I don't like it, but still I have to live with it. BMPs, you heard about BMPs, they're very common. VMPs are the management practices to control erosion in the construction site. So the idea is to do whatever is necessary mechanically and otherwise to make sure that the sediment does not leave the premises, that it stays there. A case in point, the Aguaje de la Tuna River in Tijuana that I've shown you. I recently shown you a picture of that. That was 1993. But what happened was that 2 years earlier, in 1991, they had another flood in the Aguaje de la Tuna. And then the engineers decided, the engineers came up to analyze what to do. And every time there's a huge flood and there's a lot of damage involved, the engineers, the flood engineers, are called on to give an opinion as to what should be done. How should we manage this? How should we minimize the movement of sediment? We don't want the sediment to move, right? So they decided, in their wisdom at the time, I wasn't there, they decided to create or retain the sediment. They said, we're going to hold on to the sediment because we don't mind too much if the water gets to the valley, because the water gets in and it gets out. But the sediment, once it gets in, it doesn't want to get out. We're going to have to haul it. If it gets into the living room, a couple of feet of sediment, not even have to be a couple of feet, just 6 inches will be bad in your living room. Can you imagine? And that happened. So the Mexicans, the people in Tijuana, the engineers, they decided that they could not, if they had another flood, and they could not tell when, but it could be like next 3 years, next 5 years, that they were going to hold on to the sediment and let the water go by. That, of course, in retrospect, was a huge mistake. But they did it because they did not know the lane relation. They were civil engineers, but they were not hydraulic engineers, let alone they were not sedimentation engineers. Because within the field of civil engineers, for 1,000 civil engineers, you have maybe 50 hydraulic engineers. And among those 50 hydraulic engineers, we got 1 or 2, perhaps 3 sedimentation engineers, which is what you guys are learning to do now. You're a very small number among all the civil engineers that went to school with you whenever they did, maybe 20, 30 years ago. So you're going to know a lot about a rather specialized field. At the time, they didn't know, so they went ahead and built these 2 sediment retention basins. They call it sediment retention basins. The rationale is the flood is going to come and it's going to carry a lot of sediment, and we know how much because we can calculate that. That has been done. I'll talk about that later. How much can the sediment, during a flood, how much sediment can you expect from the water that is moving swiftly at this time? When it used to move like a foot or 2 feet per second, now it's moving at 5 feet per second, right? So it's carrying a lot of sediment. So they were successful in the year 1992, by the way, in building the 2 dams. And I have pictures of that. I'll show it to you later on. And in 1993, lo and behold, they were tested 2 years later, only 2 years later. Nature could have been nicer to them and wait 10 years for that to happen, but she wasn't. She says, aha, you guys are defying me. I'm going to challenge you. So she went ahead and sent the second huge flood in the region in the year 1993. It was January 7th. I remember that because I was out of town. I was in Peru, actually, or South America, in Brazil. I don't know where I was, but it was the summer. I mean, not sorry. It was January 7th. So it was during the break, because we have a break. January, beginning 2-3 weeks of January is always a break, and I was always traveling. And when I came back 2-3 days later, I met my friend. I had a good friend out there, and he said, you know what, Miguel? Miguel's one of my names, by the way, Victor Miguel. You know what? He said, we had this huge flood and all this thing happened, and he showed it to me. He told me. I said, I want to go visit. I want to see it. And I had a chance to take a first look at what actually happened over there. What had happened was that the 2 dams did their job of holding on to all the sediment. Not all, but a large portion of it. Let's say it could be calculated. But it produced hungry water, quote unquote hungry water. The sediment had been taken out of its sediment, deposited in the 2 reservoirs that you have specific sediment retention reservoirs, and then it came downstream of the 2 dams hungry, and it proceeded to erode to datum, about 5 feet. That's the picture that I've shown you earlier. That did not exist. It took maybe 500 years, and I'm guessing in here because I happen to know, to produce this depth of sedimentation from here to here. It could be maybe 3 or 4 feet. I think it's 5 feet actually. We measured it. 5 feet of sedimentation, maybe 500 years or even more. God, who knows? And it took only half an hour to get rid of all that and take it downstream. Yes, it happened. 1993, January 7th, here. How do we know that this thing happened? Well, we know you can't be, I mean, you cannot negate the fact that there's rock, and the rock wasn't there before the event, right? Secondly, the sediment that had eroded from here went all the way to the mouth of the Aguaje de la Tuna, to the river. And in the mouth, it deposited 400,000 cubic meters, which is about 500,000 something on the order cubic yards of sediment that had to be removed by hand. Actually, with some of it by hand. That's another story that I'll tell you later on. But it had to be removed, and it was, of course, eventually. And that was a bad experience. That was an example. This has happened and continues to happen. In the year 2009, I had a meeting in northern Peru with the design team. And the geotech engineer, because they're in the design team, there were 7 people in the design team for this dam. And I was the hydrologist. I was not the designer of the dam because that was geotech and design, dam design, civil, it was civil. I was a hydrologist. They wouldn't trust me on the hydrologic calculations. But the group met in order to consider a problem. There was a problem. And the problem was that there was an expectation that there was going to be a lot of sediment coming up from the hill. And that is correct. This is the Andes, and they go all the way up to 5,000 feet, 5,500 feet actually. I'm sorry, meters, which is 17,000 feet. There was a lot of sediment to be calculated. And then people can actually hire me or whatever. I wasn't hired to do the sediment, but you can expect a lot of sediment. So there were 2 things in there that we considered. The first one was to build 2 dams, not 1, and manage the sediment so that it would be thrown around when the time came and the main reservoir in stream was filling up, that we could do something about it and put some water into the second reservoir and so on and so forth. That had been tried in other places and it had worked. So we were using the experience from other places and recommended that 2 dams be designed in this place. It hasn't happened yet, but it will eventually. It takes time to do these things. Everybody has to agree and the money has to be found and so forth. But then the issue was that there were still people that were thinking that there's still going to be a lot of sediment. So the geotech, the main designer of the dam, came up with the idea to build a few more dams upstream, little dams, like 10 feet, 20 feet, to hold on to the sediment, to hold on to more sediment. And he said that it was not going to be too difficult because they were small dams. So we met to decide whether this was appropriate. And I said, I don't think so, because of the lane relationship. I disagreed with the geotech engineer, with the dam designer. I said, because we know the lane relationship. If we know if you have a natural situation and you release, and I was based on my experience in Tijuana and other experiences that were not my experiences with, but were from other people. And I said, namely Lane, who was my grandfather, academic grandfather. He was the professor of Daryl Simons, who was my professor. So he had said the same thing, hungry water, you got to be careful. So then I said, there's going to be hungry water, and there are going to be holes, and then you're going to end up with nothing. You're going to spend the money for nothing. I said that in front of the geotech, who had advised that we should do that. So there was an issue of conflict in here. So-and-so said this, Professor Ponce said that. So the boss, the head of the project, said, oh, okay. So he called on the expertise of a gentleman who was a very old gentleman, about 75 at the time. This was 10 years ago. I was about 65. And he asked him the question, and he says, John Doe, what do you think? Who do you think is right here? Professor Ponce or the other gentleman? He was a geologist, not an engineer, but he had a lot of experience. He was an old man, a lot of experience. He was a practitioner with the Army Corps. He had done a lot of work with the Army Corps. And you got to realize the Army Corps personnel If anything, they have a lot of experience. I don't know what kind of experience, but a lot of experience, okay? Done a lot of projects throughout the United States. And this guy said something very simple. He said, we know that dirty water doesn't pick up a whole lot of sediment, and clean water does. So I'm going to go with Ponce on this one. So I basically won. I won the argument, and nothing was done or nothing was proposed that it be done. So as you can see, these stories about sediment abound. There's all kinds of stories on the sediment. I can tell you 10 stories, 10 more stories. So let's move on in here a little bit.
Professor, it's 6:42 if you're going to tell your other story. Your dirt eating story.
Oh gosh, yeah, thank you. I'm going to stop there. Thank you, Cassidy. You're good, you're good. My dirt eating story. In the 80s, actually, no, I take that back, in the 90s, I became a student of Humboldt. Who is Humboldt? Alexander von Humboldt. Most people in the US don't know who Humboldt is, unfortunately, because it's not of the, how can I say, the lore. Basically, it isn't. Even though California has 58 counties, and one of the counties is named after Humboldt. I'm sure you guys, many of you don't know that, but there's a Humboldt. There is even a Humboldt state in California, which is after Alexander von Humboldt, okay? But having said that, I read Humboldt. Humboldt has a lot of works, but the work that most interested me was his personal narrative. He went to South America for 5 years and came back and wrote an encyclopedia of the time of 7 volumes of natural history. 7 volumes. And I decided that I was going to get steeped in natural history because it was something I wanted to get in there. The reason for it is because I wanted to get into environmental science, environmental engineering, and because I had no background. I was a straight civil. Well, hydrologist, but straight civil. I thought water didn't have anything other than water, which is totally not true. So I decided to, it has sediment, it has nutrients, it has all kinds of stuff out there. The other one is humic substances and so forth. That's a long story. I'll come back to that later. But the point is that I decided to get into Humboldt, and I read all Humboldt, and I became very good with it. And I was fascinated by a section that spoke about geophagy. Geo is dirt, land, soil, and the land, geo. And phagy is the Greek for eating. So Humboldt in his book, I don't remember which volume, maybe 3 or 4, dedicated part of about 3 or 4 pages of his book to describing how the Indians, the natives of Peru in the jungle, because he traversed the jungle. He was interested mostly in the jungle. Eventually he got everywhere, but the jungle was his prime interest at the time, because he felt quite correctly that nobody in Europe knew anything about the jungle. Don't forget that I'm talking about 1803, 1804. So he felt that he was going to go out there and discover, and he did discover a heck of a lot of things. One of the things that he discovered was that the Indians out there were eating dirt. Eating dirt. I thought that was, yucky. How could they do that? But I realized at the time that Humboldt was correct in putting that out as a big thing, because he had to do with the nutrients, and Humboldt was interested in everything, particularly the nutrients. And at that time, my interest in this whole thing of holism was being developed. So I felt that this is fascinating. So then I started believing what Humboldt had said, and I had no reason to doubt what he said, because his stuff was based on experience. He saw a whole lot of people out there going to the river, getting a little bit of river with water of the river from a little bit of sand and silt, mostly silt actually in the river, and they were choosing the soil, and they drinking it because they felt that it was necessary. And don't forget that these are people that are natives. They are Stone Age people. So if they want to get nutrients into their body, they can't go to the pharmacy and say, hey, I want some magnesium or I want some potassium. No, they got to do it. If they're going to survive nature, they're going to do it on their own. And they were doing it on their own by drinking or eating soil. Eating soil. So then many years later, I went over there. I visited southern Peru in Puno. with my family. We were out there visiting, a tour. And I went to the small place and they offered me some soil. And I took it. I took it because I was already familiar with it. If I had not been familiar with it, it was like, soil to me? No, heck, get out of here. But I was already familiar with and I wanted to experiment it. So they gave me this thing that it was like butter, but it was rock. It had been treated to kind of dissolve, but it was rock. In other words, it had been like shale, and now it was converted to some kind of butter. It was colored gray, and they offered it to me in a piece of of um, just a little piece of bread, and I had it, and I'm still here. Okay, nothing happened to me, and I ate rock, dirt, because following what Humboldt had said, that these very primitive people were actually doing that in order to keep healthy. Now, I don't know if you agree with what I said or you disagree, whatever, but I am referring to Humboldt. Later on, or about that time, I decided to paraphrase Humboldt, and I wrote a paper on it, on geophagy, as a matter of fact. And I have it on the web. So I'm going to, for those of you that are interested, and I'm assuming that not all of you would be, but for those of you that are interested, I'm going to send you a link to that paper. Because what I did in there is that I basically paraphrased, I copied, I reported on what Humboldt had done. But how, by the way, I'm telling you, I'm over my time here. I'm going to finish in a minute. Humboldt is a great guy. He's so great that he was the forerunner to Darwin. People that know say that Darwin went on his trip around South America because he wanted to be Humboldt again or do Humboldt. Humboldt was a generation removed from Darwin, meaning at least 50 years older. Okay? Humboldt was doing his work in the early 1800s, 1805. And Darwin went to South America in 1831. Suffice it to say, I'm going to finish it here because I don't want to go longer. Suffice it to say that Humboldt had not existed, maybe Darwin would not felt that he would going to emulate Humboldt, and he would not have gone on his famous trip on the Beagle around South America and discover what we already now call evolution. We will be back 200 years thinking that there was no evolution. So with that, I'm going to finish. At this point, thanks, Cassidy. So I will stop in here and I will continue on Thursday. Okay? Thank you. Bye-bye.
Thank you.
Thank
Bye-bye.
you.
Okay, bye-bye. I hope you enjoyed the lecture today. It was interesting.